And no one knows what it's like to be the Batmans, to be the sad man behind the mask. Okay, we're here to talk about the energy we can store in the B field, or a magnetic field, of an inductor, like a solenoid. So if you go back to a prior video where we looked at RL circuits, we would have seen the circuit setup where here's some EMF, here is some resistor R, and here is some inductor L. And if we went through the Kirchhoff loop, we'd have seen that setup read something along the lines of that the EMF is equal to L di dt plus IR. Okay? Now, what we're going to do here is something a little interesting. We're going to just kind of multiply, just for funsies at first. We're just going to multiply for funsies by a current. And I'm going to square that one there so we can see that. Now, why would I do this? Well, we're going to see a few things here. One, remember an EMF is just a voltage, which means that I times V, that's power, PIV, right? Now, this power is equal to something, which we'll come back to, and then plus I squared R. Well, the I squared R term here, this is the amount of energy lost through a resistor. We can call this thermal or heat energy. It's what you're losing, okay? It's energy that's lost. The last piece that we have here, this Li di dt, this is the energy stored in the B field. Okay? That's the energy that we are actually storing inside of the inductor. Okay? And it's important to think about that, this EI here, we could actually, if we wanted to write it in a slightly different way, we can call it dq dt multiplied by an EMF. Remember, the differential form of current is dq dt. It's some amount of charge passing through some amount of time. So what we could do here then is we could say the following. If we're taking a differential amount of charge through a voltage, or if we kind of write this in an even slightly different way, if we say we have a small amount of charge that we're moving through a voltage, if we remember Q times V is some amount of energy. So I guess maybe we shouldn't call this power here. Maybe we should call this energy, okay? But we really think of that as like a power output, but it's the energy output. Because Q times V gives us some energy here. But it's a differential piece of that energy. It's going to be some small piece of it. So if we take a look at that small piece of energy and we compare it to what we're storing in the B field, we can say that a small portion of energy for the B field as a function of time dt, and that's, from this idea up here, like, hey, we're taking a small piece of it just for a B field. That's going to be equal to Li di dt. And if we notice the dt's are on both sides and we quickly take the integral, you quickly will see that for a basic integral, we're going to find that the B field stored, or the energy of the B field stored in that inductor, is just going to be equal to Li squared over 2. That's our energy stored in a B field. This actually looks very similar to the energy stored in the electric field for something like a capacitor, which, if we recall, was Q squared over 2C. In this case, the I's have just, become Q's, or Q's have become I's. The 2's are the same. And in this case, the L has substituted for 1 over C. Okay, so it's a very similar equation there. Now, if we wanted to, and we won't need it for this class, but if you wanted to be more complete with everything, you could actually find what's known as the magnetic energy density inside of the inductor as well. What we kind of start with here is if we wanted to find like the density, and what we use for this, it's kind of weird. We're going to start using a small u for this, an energy field density. Sometimes in books you'll see this written with like a W, but I like to write it as UB, little UB. We're just going to call this a energy density per some amount of volume here. And that means that it's going to be some energy density divided by some cross-sectional area of the loop itself multiplied by some length, because an area multiplied by a length is going to give me a volume. Now, what we can also say is that we know what this value is here. This is the Li squared over 2. So we can rewrite our magnetic field density as saying Li squared over 2 and this is little l, this is length. Don't confuse length and inductance here. If you go ahead and do this, and you know that this L is for a solenoid, you could actually expand this even further. If you haven't seen the inductance of a solenoid here, you could sub in this L over L here, solenoid per unit length, for that value. And what we'd get out of this is going to be a mu naught turn density squared, little n, times the current squared all over 2. And what we can also see from this is that if we take this and break it a little further, what we'll find is that this magnetic flux density can be rewritten as B squared over 2 mu naught. This is just doing some more substitution with this up here, with some old equations. Now, we derived this for a solenoid, this flux density, or that's not flux density, this B field energy density, but this will actually apply to any B field. Okay, this will apply to any B field. The energy density of it will be the B field squared divided by 2 mu naught. And just as we saw up here with the energies looking very similar to electric fields, if you actually do this, the energy density of an electric field, this was 1/2 epsilon naught E squared. So it looks very similar. You still have the 1/2. The eps and mu naughts have just kind of flipped denominators and numerators, and the B squared is just replaced with an E squared. So that's kind of a thing that happens as well. So these are the 4 equations that can exist. We'll really only use these ones this year. The ones down here in blue, these are just like neat things to know in case you're doing something with that future on. But this is the idea of, in that B field, there is a stored energy. Okay, that energy is stored in the B field. It can do work out of that, which is an important aspect for us to think about as we're going through and talking about these inductances. Okay, so with that, this video is finished. There's not much more to do in the world of inductors here. We'll start to be looking into some free response problems in a little bit, and if you haven't, make sure you check out those videos located in the Coach Botzer YouTube page here. But at this point, we've done RC circuits, and if you haven't seen those, go back and check them out. We've done RL circuits, so that's done for us, but we haven't combined yet our inductors and capacitors. And when we do that, we're going to find something really weird is going to happen. So we're going to have to go back in time a little bit, and let's take a look at some harmonic motion before we get back into this idea of LC circuits. Okay? But for now, adios everybody, and take it easy.